Okay, so this is chapter 14. We're going to start chapter 14. As you all know, I wasn't in class on Friday, but I thought I'd go ahead and record a screencast of the 14 initial sections, just in case you wanted to go back and hear what I have to say about those particular topics. So on Friday, you should have started talking about aromatic compounds, talking about the molecule benzene, a little bit on nomenclature, talk about some of the reactions of benzene and the stability of benzene and what it means to be aromatic. So it turns out that benzene is the simplest aromatic hydrocarbon. As you'll recall, that functional group is also known as an arene. Benzene has 4 degrees of unsaturation, making it a highly unsaturated hydrocarbon. And if you look at the structure of benzene, you can see it's C6H6, and we get the 4 units of unsaturation because we have a single ring, so that's 1 unit of unsaturation, plus the 3 double bonds. Now, one of the interesting things about benzene is that if we take benzene and we place into that bromine, we don't see a reaction. In fact, what happens is you just start to, as you add the bromine into the benzene liquid, you get a brownish orange liquid. No addition across these carbon-carbon double bonds occurs because benzene is aromatic, and aromatic compounds don't undergo addition chemistry like an alkene will. So as you'll recall, you can take an alkene. For example, here we're taking ethylene, and if you add bromine, you get a vicinal dihalide, an addition product. Well, aromatic compounds don't do addition chemistry. They do chemistry, but they don't do addition chemistry like typical alkenes do. If we look at the structure of benzene, you might predict, in fact, that you would have a long bond, this carbon-carbon single bond, and then you'd have a shorter bond, this carbon-carbon double bond, and that would alternate throughout the structure. And so you might expect, if you exaggerated that benzene would look something like what we see over here, 3 long bonds and 3 short bonds. However, when we look at benzene spectroscopically and look at its structure, we find that all the carbon-carbon bonds are actually of equal length. So this carbon-carbon bond is actually of equal length to this carbon-carbon bond. And the way that we can account for that is through the different resonance structures that we can draw. We also find that benzene is a planar molecule. All of the carbons lie within the plane of the board as we have here. Some texts will actually draw benzene with a circle in the middle, so the 6 carbons and the circle in the middle. Kind of looks like a bolt, looking at a bolt head on, a hex head bolt. This circle represents the 6 pi electrons that are distributed throughout the entire ring due to resonance. So this is kind of like the resonance hybrid of benzene. A lot of texts do this because that actually shows that all of the carbon-carbon bonds are going to be of equal length. Again, due to resonance, we see that all of the carbon-carbon bond lengths are going to be equal, of 1.39 angstroms, which puts it right in between a typical carbon-carbon single bond and a typical carbon-carbon double bond, as you might predict. So each one of these bonds has some double bond character and some single bond character associated with them. You can see here that benzene is a planar molecule. Each carbon atom is trigonal planar with the 120 degree bond angle that you might expect is shown. Each carbon atom has a p orbital with an electron in it. And so each carbon is sp hybridized. Each one has a p orbital, and they contain, in this pi system, a total of 6 pi electrons. A little bit of nomenclature. There's some common names that you need to be aware of. If you have a single substituent, you will name the alkyl group that's attached and then add the word benzene to the end. So if you look at this particular molecule, you can see that this is an ethyl group connected to benzene, so we call it ethylbenzene. This is a tert-butyl group, so it's known as tert-butylbenzene. And this, of course, is a chloro group, or chlorine, right? So we call it chlorobenzene. There are some common names that you also have to learn. So, for example, you might look at this molecule and say, well, that should be methylbenzene. And in fact, that's not an incorrect way to name it. However, methylbenzene is more commonly known as toluene. Toluene is the molecule that's used in a number of paint thinners, a number of fingernail polish type removers, that kind of stuff. It's a very useful aromatic organic hydrocarbon that's used for a variety of purposes. This, of course, is the hydroxy group. Okay, it's kind of like an alcohol, right? And so you might expect to call it hydroxybenzene, but in fact, this is known as phenol. And then aminobenzene, we don't call it aminobenzene, although there's nothing wrong with calling it that, but the common name for this is aniline. When you have more than one substituent on a ring, it does matter how we name them. So let's look at the dibromobenzene derivatives. So here we have benzene with two bromine groups. And if you notice, we start numbering at 1, we would number 1, 2, 3, 4, 5, 6. So this would be 1,2 dibromobenzene. But in organic nomenclature, when you have two groups that are in this 1,2 relationship to one another, we call it ortho. So this is ortho dibromobenzene. We can also have the bromines in a 1,3 relationship. This is known as meta, so we call this meta-dibromobenzene. And when we have the bromines in this 1,4 relationship, we could call it 1,4-dibromobenzene, but it's more commonly called para-dibromobenzene. There are some interesting aromatic hydrocarbons that you need to know a little something about. So this is benzopyrene. It's a polycyclic aromatic hydrocarbon, so a lot of rings attached together, but it is one aromatic unit, and we'll talk about what makes it aromatic, or what make molecules aromatic in just a moment. And this is the molecule that gets inhaled from cigarette smoke, which of course comes from the tobacco plant. So the tobacco plant makes the tobacco product, and then upon burning you get benzoapyrene, which is a molecule that gets oxidized to other carcinogenic products. Some other interesting, this is the molecule Zoloft, and as you can see here, we have a benzene ring here, and we have a benzene ring here. This is a psychotherapeutic drug. It's one of the most widely prescribed antidepressants on the market today. I do believe it's a billion-dollar drug. Here is Valium. Again, you can see the two aromatic rings. This is a very powerful sedative. This molecule, Novocaine, also known as Procaine, this is the local anesthetic that you might encounter when you go to the dentist before they give you a shot in your mouth. It gives you that local numbing sensation that is so important before they actually give you the shot in the mouth. Viracept, this is a anti-HIV drug, or antiviral. Again, you can see we have more than one aromatic ring in this molecule. This is Viagra. So again, you can see the aromatic ring within Viagra. And then Claritin. You can see that we have two different aromatic rings here. We have a purely hydrocarbon aromatic ring, and then here we have a hetero aromatic ring where we have a nitrogen in the middle, within the ring, excuse me. So there are two different aromatic rings within Claritin. Benzene is more stable than what you might predict, and so we can actually use heats of reaction to determine its stability. And it turns out that this unexpected stability is what actually makes an aromatic molecule aromatic. That's what we mean when we say aromatic. We mean it's a molecule of unusual stability. So for example, if you take cyclohexene and you hydrogenate it, so we're going from a pi bond to all sigma bonds, so we should release energy when we do that. And in fact, that's what we observed, and we get almost 29 kilocalories per mole of energy released in doing so. If we take 1,3 cyclohexadiene, so it's conjugated, and we hydrogenate this, we get about 55 kilocalories per mole of heat released. And what you might expect is that this would be just twice the amount, since we have two double bonds, but in fact you can see that it's a smaller amount than what you would predict because of the conjugation. As you know, conjugated systems are lower in energy than non-conjugated systems, and that's why the energy is not as you would expect. However, if you look at benzene, if you want to think of it this way, we can think of it as three double bonds. We know that it's not really three isolated double bonds, but if we think of it as three isolated double bonds and we try to hydrogenate it, what we find is that we get just shy of 50 kilocalories per mole of heat being released. Well, if we take this top value and we look at it and multiply it by 3, we should have gotten about 86 kilocalories per mole of energy. And the difference here is quite large. And so benzene is considerably more stable than a molecule that is just 3 isolated double bonds. And it's this added stability that makes benzene aromatic, makes it extremely stable. So if we look at some chemistry of benzene and another alkene of similar structure, so cyclohexene versus benzene, if we add the cyclohexene to a cold dilute solution of potassium permanganate, we find that we actually get rapid dihydroxylation. So we end up forming the diol, as you might expect. That happens very, very quickly, and this will decolorize the solution of potassium permanganate. It'll go from purple to clear. However, when we add benzene, we observe no reaction. If we add bromine to a solution of the alkene, we find that we get rapid addition and the bromine color disappears. However, if we add bromine to benzene, we find that no reaction occurs. So benzene doesn't do addition reactions. Same type of chemistry, if we try to add HX across the double bond, we find that for the cycloalkene that happens very rapidly. For benzene, no reaction. We can also add hydrogen across the carbon-carbon double bond of cyclohexene very, very easily. 20 pounds of hydrogen pressure, which isn't very much. Room temperature, hydrogenation occurs very, very quickly. If we tried to do that with benzene, we would find that no reaction actually occurs. But if we take the temperature of benzene up to about 100 degrees Celsius and put 1,500 pounds of pressure of hydrogen on it, we can actually reduce benzene to cyclohexane, but it does occur very, very slowly. So again, showing there's a big difference between these aromatic hydrocarbons and other hydrocarbons. So like I said, benzene will not undergo an addition reaction. We can't add bromine across the carbon-carbon double bond, if you will, of the aromatic ring. Addition chemistry does not occur. However, in the presence of the right reagent, so here we have bromine and iron tribromide, we can actually do a substitution reaction. So we can replace the hydrogen of a benzene with a bromine. That type of chemistry can occur. And if you look at it, what you will notice is that you have an aromatic ring on the left and an aromatic ring on the right. So we're not losing the aromatic stability. However, in this top example, you can see that we have an aromatic ring on the left, but we don't have an aromatic ring on the right because we don't have the 3 double bonds shown in there. And so we're losing that added stability here, and that's why benzene doesn't undergo these normal addition reactions that you might expect from an unsaturated hydrocarbon. So what does it mean to be aromatic? Well, we know that it means to have this unusual stability, but it turns out that we can follow what are known as Huckel's rules. And there are 4 criteria that must be satisfied for a compound to be aromatic. All 4 of these criteria must be satisfied. Rule number 1 is the molecule must be cyclic, meaning that if we start at a carbon, if we took our pencil and went all the way around, we would end up where we started without ever lifting our pencil. So in this particular case, this 6-membered ring would satisfy that criteria. It is clearly a cyclic molecule. However, if we look at this molecule, you'll notice that starting at this carbon, I can go all the way around to this carbon, but I can't get back to where I started without lifting my pencil from the page and putting it at the starting point. So this is a not aromatic system or non-aromatic system, whereas this one on the left, being cyclic, would be aromatic. And the reason that it has to be cyclic is so that all the p orbitals can actually overlap one another and come into contact. The second rule is that the molecule must be planar. All the atoms of the molecule must lie within the plane, or at least all the atoms within the aromatic portion of the molecule must lie in a plane. And so, for example, benzene, as we mentioned before, it's completely planar. All 6 carbon atoms lie in the plane. We have to be kind of careful here because if you look at cyclooctatetraene, you might predict that all of these carbon atoms are in the plane. But when you build a model, you'll actually find out that it takes on a tub shape. Okay, and so since it's not a planar molecule, even though as we have it drawn here, it looks like all of the carbon-carbon double bonds are in conjugation with one another, it's not aromatic, and it can do just traditional addition chemistry, just like a normal alkene will do. So you can actually add bromine across the carbon-carbon double bond. Rule number 3 is the molecule must be completely conjugated. That is, each and every one of the atoms within the aromatic ring has to have a p orbital on it. And so if we look at benzene, we'll notice that each and every carbon atom is sp2 hybridized, meaning that there is a p orbital on each and every one of these carbon atoms. However, if we look at 1,3-cyclohexadiene, we notice that there are only p orbitals on carbons 1, 2, 3, and 4. 5 and 6 have no p orbitals, and so it's not a cyclic conjugated system. Yes, it's completely conjugated here, but it needs to be completely conjugated throughout the ring to be an aromatic system like benzene would have. And then rule 4, the molecule has to have a certain number of pi electrons. And the pi electrons have to equal 4n plus 2, where n is some integer. Okay, so for benzene, for example, 4n plus 2, right, is equal to 6 pi electrons. And if we solve for n, we find that n is equal to 1. Well, n satisfies an integer, and so it's an aromatic compound. Okay. If, however, we look at cyclobutadiene, we find that the 4 pi electrons does not equal 4n plus 2. There's no integer that you can put in for n that would make that satisfy Huckel's rule. This satisfies, however, the 4n rule, so 4 times n equals 4 pi electrons if n is 1. But 4n equaling the number of pi electrons actually makes this an anti-aromatic compound, and you can read about that more in your text. Very, very important. All aromatic molecules must satisfy all 4 criteria for aromaticity. If a molecule fails one of those criteria, it's not aromatic. So to give you an idea of the number of pi electrons that will satisfy Huckel's rule, you can, for n equals 0, you can have 2 pi electrons, 6 pi electrons, 10 pi electrons, 14 pi electrons, 18 pi electrons, so on and so forth. You can go through and solve for each value of n pretty easily. There are other rings that are much larger than benzene that are aromatic. For example, these types of molecules, these annulenes. This is known as 14-annuline because there are 14 carbon atoms in the ring. If we count up all the pi electrons, we'll see that there's 2, 4, 6, 8, 10, 12, 14. 4n plus 2 equal 14 when n is equal to 3. That's an integer. This is an aromatic compound. Each and every carbon atom has a p orbital. If you build the model, you'll actually find that it lies in a plane. 18-annuline, also the same story. If we look at cyclobutadiene versus benzene, cyclobutadiene is actually anti-aromatic, meaning that it's less stable than you might predict. And benzene, of course, is aromatic, as we've discussed, and means that it's more stable than you might predict. However, if you look at the models of both of these, you'll find that both are cyclic, both are planar, and both are completely conjugated. However, benzene's the only one that satisfies Huckel's rule for 4n plus 2 equaling the number of pi electrons. Cyclobutadiene satisfies the 4n rule, so it's anti-aromatic. The way that we account for this difference is based on molecular orbital theory. And so we can actually get the molecular orbitals for aromatic compounds by doing what's known as the Frost circle or the inscribed polygon method. So what you do is you draw the shape of the molecule where at least one of the vertices is pointing directly down. and you draw a circle around that. And everywhere that circle touches a point on the structure that you've drawn, that's going to be the relative energy of an orbital. And so if we put in our orbitals, we'd have an orbital here, we'd have two degenerate orbitals here, two degenerate orbitals here, and an orbital here. And if we put in our electrons, our pi electrons, we know that benzene has 6 pi electrons. We put 2 electrons here, 2 here, and 2 here. And all of those electrons are below this line that runs halfway through the molecule, meaning that all of the bonding orbitals are full. We're not filling up any of the anti-bonding or non-bonding molecular orbitals, and that accounts for the aromatic stability of benzene. So I want you to think about this particular problem. This, of course, isn't a quiz, but I want you to think about why a free radical will abstract a hydrogen from this carbon and give us this product, and not abstract a hydrogen from this carbon to give us this product. So think about that, and I will see you all next week.